I'd like to thank all of you for coming. We have two prominent speakers from JPL. I think it was a coincidence they both turned out to be JPL, but they are right up at the latest information on earth science, and one's going to talk about rising sea, and the other's going to be talking about our groundwater going down. So we're going to get, from one hand we'll have too much, and the other hand not enough. Each speaker is going to have 45 minutes. We can be a little loose with that, and then we're going to set aside 10 minutes for question and answer after each speaker. And would ask you not to interrupt during the talk, but jot down your thought if you have a question, and remember to ask it when we get into the Q&A period. Ian Fenty received his PhD in climate physics and chemistry from MIT, and then joined NASA JPL as a climate scientist. As part of his research, Dr. Fenty collaborates with JPL oceanographers, glaciologists, and other scientists to reconstruct the circulation of the Earth's high-latitude oceans over the past 2 decades. He's currently researching the connection between warming oceans and the melting of the Greenland ice sheets. Very current and important topic. Ian.
Thank you for inviting me to your group to speak about this issue. It's dear to my heart since I've made it my life's work to study this field. And it always excites me to know that there are people in the public, wider public, who also care about these issues. I was asked to speak about sea level rise because that's something that underpins a lot of the research that's going on right now at JPL in earth science. Okay, so I tried to make the title and the main message of this presentation very clear. And if you get nothing else from this 45 minutes, just take note of this first slide. Okay, so the highest level point is that global sea levels are rising at an accelerated rate. So they're not just rising, but the rate of the rising is increasing, okay? And we can attribute this rising and its acceleration to 2 sources, all right? The first one is thermal expansion of ocean water as the oceans warm, okay? Things expand when they warm up. The oceans are warming, they're expanding. The expansion is mostly manifest in the vertical direction, so that increases sea level. The second point is the transfer, a net transfer of water from land to the ocean due to the melting of mountain glaciers and the Greenland and Antarctic ice sheets. Okay, so this is water that was once in the ocean, is now trapped on land in the form of ice, that's melting and flowing into the seas, raising the bathtub. It's the simplest analogy. So there's the 2 major sources on the decadal time scale, 10-year or longer time scale. It's those 2. So why do we care about sea level rise? Well, I just moved to Altadena. I don't really care about sea level rise. My ears pop when I go home. But sea level rise, changing wave climates, and storms are placing additional stresses on coastal systems worldwide. And I used to live in Venice when I first moved to California, and I would ride my bike past this power plant in El Segundo. Right, this is the El Segundo liquid natural gas power plant, which is meters, or rather feet, away from the beach. Right. And estimates say that about $1.4 trillion, that's an unbelievable amount of money, of coastal property could be at risk at high tide by the end of the century. Coastal flooding from sea level rise could displace 200 million people by the end of the century. And I like this figure, although it's kind of hard to see. Every little circle on there is a city that was identified as the most vulnerable, with the people with the most vulnerable populations to sea level rise, okay? And oftentimes global disasters don't affect us in the first world. But in fact, sea level rise is expected to, especially for our friends, my retired father, for example, in Florida. And, but specifically there's a cluster of cities that are very low elevation, in Southeast Asia. Okay, so.
What about the ocean, the islands?
Oh yeah, sure. Well, those aren't major cities. Those are whole populations and societies and cultures. In fact, just yesterday I gave a talk to National Park Service, and there was a representative from Samoa. Yeah. Just an event which isn't even directly related to sea level rise, but just was the fortuitous combination of two weather events, a very high tide and a hurricane in New York a few years ago. Hurricane Sandy caused $50 billion in damage in just one event, right? My uncle couldn't leave his apartment building for 3 days. Estimates are 500,000 people, 1 million jobs, and $100 billion of property are threatened by climate change along just the California coast over the next century. And this is a stunning picture. I apologize in advance now for people in the back who can't see anything on the bottom. But this is a famous picture that was taken during the El Nino of 97-98 that shows a house in Laguna Niguel that fell off the cliff because of coastal erosion, right? So we expect that as sea levels rise, the coast will become more vulnerable to storms and flooding, which will enhance this coastal erosion and take some of our friends' beautiful beachfront houses with them. Okay? Now, just 2 days ago, this story came out in the Guardian. It's been talked about for a while in sea level circles. There's a small, low-lying island of resettled indigenous people in Louisiana. Okay? And this island has lost 98% of its land over the past few years due to rising sea levels. Okay, so it was just above sea level, right, like a delta marsh kind of situation. And so even a small amount of sea level rise can completely wipe this place out. So the US government, via Louisiana State, is paying to relocate everybody on this island, right? $50 million. Here's a great quote. With this federal funding, the people of this island will be the first program in the lower 48 states to address an entire community's resettlement due to climate change. And they say the lower 48 states because we've already allocated money to an indigenous group of people in an island off in the Arctic Ocean. All right. But we don't hear about that because they're indigenous and there's a small population, right? But this is the first one in the continental U.S. All right, and this is another great quote. This article is full of great quotes. You can still find it online tomorrow or tonight when you get home. The project will be watched closely as a testing ground for the resettlement of whole communities as the effects of climate change are felt more acutely along the coast of North America. So not everyone on this island wants to go. Okay, you grow up here, this is where your friends and family are, right? You don't want to move. You know what that feels like. The tribe twice voted against being relocated, right? And no one's being forced to move, but it's an eventuality where people are going to move. This is a sign on someone's front yard that says we are not moving off of this island, right? But it's just a matter of time. Okay? So, sea level rise is a major societal issue. NASA takes it very seriously. And I'll just pitch some pro-NASA propaganda at you. I love this quote. It's a good quote. NASA uses the vantage point of space to understand our home planet. And what I love about this animation is that every slice of this rotating beach ball is data from a NASA satellite that we can put together and make a comprehensive reconstruction of what's happening to Earth's oceans, land, and atmosphere. Okay? This is, this one here is the amount of water that could rain, the cloudiness, the actual precipitation, the moisture of soil, which Dr. Calmietti will talk about, the biosphere, and this next one here is the currents of the ocean. So we put all these together to be able to make, to really be able to understand our home planet, okay, and sea level rise is one of those major issues. And because it's such a major issue, and because the oceans play such an important role in sea level rise, there's a whole specialized set of satellites that whose only job, they have only one job: measure the elevation of the sea surface. Okay, and actually, I can trace my entire higher education to this satellite. Okay, because in graduate school, my advisor worked on this first altimeter, TOPEX Poseidon, and the money from that project funded my entire graduate school, my postdoc, and even today, it is a huge part of my professional life. So we've had NASA has had 4 of these instruments. 2 currently exist. One just recently launched from Vandenberg on a SpaceX rocket a few months back, actually in January. So concurrently, NASA has these 2. Other nations have their own, okay? But these altimeters, here's a nice little picture. These altimeters work in the following way. While they're in orbit, they send down a radar pulse to the surface of the ocean, which bounces back, and you know the speed of light, and you know where the satellite is from GPS, so then you can back out how far away the sea surface is, okay? That's a simple principle. So that as the satellite travels around the world, it bounces the radar down, and wherever the elevation is, it then reflects back up, and it detects that time difference. All right, what does it look like when you put these maps together? It's really mind-blowing. This is an animation showing the changing elevation of the sea surface globally from 1992 until 2011. Okay, and I think every frame might be, let's call it 1 day. All right. So sea levels on Earth are not what you might expect. They're not a static thing, right? Sea level on Earth is an amazingly complicated thing, which is essentially at the, to understand what's happening in this picture, you need a PhD in oceanography, right? It's no joke. Literally thousands of oceanographers work to understand the processes that create this changing pattern that is the ocean surface elevation. But I said sea levels are rising, so what does it look like when you take the long-term view, you average all of that data together? What is the difference? And this is the pattern of sea level rise on Earth measured by NASA altimeters from '92, when TOPEX Poseidon first launched, until the recent past. Okay? So what I like about this picture is that it quickly conveys the fact that sea level rise is not uniform. All right? We talk about global sea levels rising, but it's not uniform. There are certainly places that have had much greater sea level rise, for example, the Western Tropical Pacific, and places that have somehow dodged the bullet of sea level rise, i.e. Los Angeles. All right? So there are plenty of reasons why the pattern looks like the way it does. The single biggest reason is the redistribution of ocean heat within the ocean. All right, so ocean currents and the heat in the ocean, it moves around. All right, and that movement changes from year to year. All right, so where, for example, in the Western Tropical Pacific, it shows a large positive rise in sea level, it indicates that, mostly indicates that those waters have warmed the most. All right, but the heat for those waters didn't all come, say, from global warming. Some of it came from the Eastern Tropical Pacific, which is why, in part, we have lower sea levels now than we did 20 years ago. All right, but the exchange of heat within the ocean is, in some broad sense, cyclical. What went away over the last 20 years will come back. All right, and then when that happens, local sea level rise will spike. Whereas it's been flat or negative over the last few decades. Okay. And let's put a scale on it. Where it's deep red is about 3 inches. Okay, so these are it's very difficult to think about this because the spatial scales are so huge. The vertical scales are so small, right? But that's all it is, 3 inches, okay? All right, let's take that map, let's collapse it to a single time series. All right, a single time series that shows the change in global sea levels since 1900. Okay, so before humanity had the ability to monitor sea levels from space, we have to rely on less fancy methods like tide gauges. Okay, the global tide gauge network and other proxies, all right, other indirect proxies, and indirect proxies, allow us to make this plot. On the x-axis is time, and the vertical axis is the sea level change in inches, all right? And what's blue is the record that we get from the tide gauges, and what's red is what we are able to observe from outer space, all right? So some of you, many of you probably work with data and statistics. So it will not surprise you, there is some controversy in the lines that are drawn on this plot, okay? In that they're trend lines, okay? And the drawing of trend lines is very sensitive to the motivation of the statistician who happens to be behind the desk, right? But we, so I admit, I just recognize that and state it, okay? According to this author, all right, and he's a well-respected author, there's nothing controversial about this, okay? In his group, they identify three, let's say, epochs of sea level rise since 1900, okay? And that's why they divided it into these three lines, all right? The first, the first epoch from 1900 to 1930 is a period of relatively low sea level rise. And then, let's see if I got my animation right here, boom. Then the rate of sea level rise more than doubled, okay, over the period 1930 to about 1992, all right? Then it more than doubles a second time, okay, from 1992 until present. So you see that the slope, right, this is the sea level rise slope, today is significantly faster than it was at the beginning of the last century, all right? So I hate suspense. So that's the answer. This is the answer to the question: why are sea levels changing, and what's caused the recent increase? Okay. Today, this is the actual proportion. Okay, the actual proportions of the different contributors to sea level rise, right? A little bit more than a third of each in the melting of the polar ice sheets and mountain glaciers, okay, and the remainder with the thermal expansion of the oceans. So the thing that changed in these three epochs is namely the melting of the polar ice sheets, okay? That is the single biggest contributor to the jump, all right? Although it's also true that there is more heat going into the oceans, and so thermal expansion is also increasing. All right. So now we're going to spend a little bit of time and break into those three pieces of the pie, because I think they're interesting, and I'm just assuming you do too. But because these all have to do with things of warming and melting, let's just spend 1 minute talking about what global warming is and why it's caused. You guys are amongst the most educated groups that I get to speak to. So I am sure you have all at least read an article once about what the greenhouse effect is, but this is the best schematic that I ever use, my favorite schematic to show it, okay? So the idea is the sun sends radiation to Earth, and some of that radiation hits the atmosphere and scatters back into space. Some of that radiation hits the surface of the Earth and scatters back into space, okay? So we just forget about that as lost. Some of that radiation comes to the Earth's surface and warms the Earth, okay? And then a very basic principle of physics is that warm things radiate energy back out, okay? So the Earth radiates this energy back out at a different wavelength, at a lower wavelength than it was absorbed. So this is called infrared radiation, okay? It's the same principle that is used in an infrared camera, maybe to identify a burglar or, in warfare. So this warm Earth radiates energy back into space. If there were no atmosphere, all of that energy would go back into space. But because we have an atmosphere with certain gases, some of that energy is absorbed in the atmosphere, okay, and then re-emitted. It's like I throw a ball to you, and you throw the ball in some random direction. Sometimes you throw that ball back into outer space, it keeps going. But sometimes you throw that ball back down to Earth, all right? So when that ball comes back down to Earth, it warms up the Earth again, okay? So the Earth gets like twice the impact for that single bit of radiation from the sun. So this is the normal situation. Now what the greenhouse effect is an increase in the absorptivity of the atmosphere to that outgoing radiation, all right? So basically it's a blanket that we put on the Earth. When the energy goes back out, now there are more catchers for it, essentially. More people who are catching the energy going back out and throwing it back down to the Earth, all right? So, this is what, global warming is all about, all right? The principal gas that humans emit that cause this increase in the absorptivity and downward transmission of long-wave radiation back to the Earth is CO2, right? That's why we all drive Priuses, right? This is CO2, and this is a super famous chart, right? This chart began in the late 50s by I think he was a Scripps, and then he was a CalTech or CalTech and Scripps scientist, Ralph Keeling, and what he did was he went to a place that was unaffected by industry, right? He went out to a mountain in Hawaii, Mount Mauna Loa, and he put up this instrument. He created and put out this instrument that records the amount of CO2 in the atmosphere. All right, so this is a stunning picture that shows that over this entire record, we've had a steady, oftentimes increasing, the rate also increases, amount of CO2 in the atmosphere. Okay, so, also Basic Physics 101 established in the 19th century, or perhaps earlier, tells us that when the CO2 is in the atmosphere, global warming will occur, all right? So, we all read the paper, and we read about record heat, all right? Records being broken all the time, heat waves. The pattern of global warming, just like the pattern of sea level rise, is not uniform across the Earth, all right? There are some places that get more warming than others, and this is like this is the most recent map of temperature anomalies for Earth, right? This is as of March of this year. Okay, I downloaded it last night, right? So where it's dark red, these are places that are having the record warmest temperatures in that month ever, all right? So, we can run a movie like this through time, and we'll see record warming happening all over the US, all over all the continents, all over the oceans. But this is just what it looks like 2 months ago, all right? So this is one of the pieces of evidence of global warming. Now there's another plot, which is also super important, that you have seen in one form or another, and it's this plot rather, which shows the average temperature of the surface of the entire Earth, okay, from 1880 until today. And of course, we can draw trend lines through here, pick a starting point, pick an ending point, all right? So I think it's about 0.07 degrees Celsius per decade. But that's irrelevant. The point is that over this time period, it's going up, and the latest IPCC report, the consensus is that since 1950, most of the warming that has taken place is due to human activity. Okay? Now there's another interesting feature of this plot, which I think deserves some mention, and one is that it's not steady up. Okay? So I'm going to click here in the early part of the 20th century. Temperatures were pretty flat, And then there was a period when global warming seemed to be happening at a high rate. Then there were a few decades when it was flat. And then again, a period of warming followed by a recent period of seeming flatness, which was referred to by many climate skeptics as the hiatus, or evidence that all the climate scientists are hoaxsters. It's my favorite, really. Of course, over the last 3 months, that has all gone away. We've had 3 months of record global temperatures on Earth. But the fact that there is a hiatus, there was one recently, really was not a surprise to any climate scientist. This is just what happens on Earth. Okay, the surface of the Earth's temperature is a very strange variable to measure for climate scientists. And why? Because the air does not hold a lot of heat. Okay, if the sun were to turn off, the Earth would lose all of its atmospheric heat in just a matter of days. It would just go out into space. Okay, the atmosphere is kind of like the tail of the dog. Okay, we live here, we care about it, but it's really not that important. All right. So during these periods of the hiatus, or rather during this whole period, where is most of the global warming going? All right, we know that more than 90% of all the warming from global warming will go into the ocean. Okay, the atmosphere here is just above 2%. Okay, so the single biggest recipient of this global warming is the ocean. All right. Now, I just made this last night. I hope it works. You know, when you look at a map of the Earth, it's usually of the U.S. and maybe it looks like this, right? So you think, yeah, there's the ocean. I love Santa Monica, you know, but it's just like that far away thing that is, you know, outside of our minds. But I just rotate my Google Earth a little bit, right, and that is what you would see. Right, this is a site which most humans don't get to see because we're not on the space station. But this is just the view from, you know, the same exact distance from the Earth, just rotated. This is the Pacific Ocean. All right? You know, we know from 5th grade geography that the Earth is 70% water, but we forget. Right? We also know the old adage of watch pot never boils, but that's because the heat capacity of water is so high, you have to put a fire on it for like 10 minutes before you can have tea, right? It takes a long time for it to heat up, right? So this figure now hopefully makes a little bit more sense. The ability of water to absorb heat is tremendous when compared to the atmosphere, and the amount of water on Earth is huge compared to the amount of mass in air, okay? So in fact, if you look at the heat of the ocean, this is a reconstruction from 1960, okay? The amount of heat in the ocean is more or less straight up, okay? And this amount of heat, that's the rate at which the oceans are warming, is 100% consistent with what we would predict based on how much CO2 is in the atmosphere, okay? There's no hiatus in the ocean, okay? Now, fun fact, because I just thought it was interesting. Again, I just assume you would think it's interesting. You know, there's a y-axis here, right? 10 to the 22 joules. That's a meaningless number, all right? Zetajoules, meaningless to all of us. I try to put some physical understanding on this, which is kind of a joke because this also has we have no physical basis of this either. But every year, the amount of new heat absorbed by the oceans due to global warming is 10 times the amount of energy harnessed from every energy source applied towards humanity's endeavors across every industrial and technological sector in every country. So, let me rephrase that. Every bit of energy humans use in total on Earth, right? Imagine what that is. For everything all humans do, everywhere, that's only 10%. of the amount of energy that's being absorbed by the ocean, right? That's to me, that's mind-blowing. I hope you also found that interesting. The expansion of seawater associated with this absorption of heat energy, right, gives you a plot like this for sea level rise, right? This is the amount of sea level rise due to the expanding oceans. I mean, of course, it follows this plot, right? It should. And so what we get is about 1.6 of the 5 inches since 1960 is attributable to this expansion of the expanding of seawater. All right, let's go on. So I showed this pie chart. I said that there were 3 major contributors. Now we'll move on to the ice sheets, the polar ice sheets, okay? You know, I talked to some school kids and many adults who don't know where Greenland is and have never heard of Antarctica. So just for fun, I put this on here. I would be remiss to not. Of course, none of us talk about Antarctica or Greenland, so you'd be forgiven if you couldn't put your finger on either one immediately. And if you didn't know some fun facts about these two places, special places on Earth, okay? Greenland and Antarctic ice sheets. All right, you can call them islands or continents, it's irrelevant. They're large pieces of land that are covered in miles of ice, all right? They're the product of a cooling Earth that has taken place over the last several tens of millions of years, okay? So let's put some numbers on it. The volume of the Greenland ice sheet, 684,000 cubic miles. The Antarctica is about 10 times that volume. And I was reluctant to put numbers like this on here, but I realized that we all live in Pasadena, so we all know what house prices cost. So these are numbers that you actually can appreciate. This is a price for a house that doesn't exist anymore. And I hope one day to meet some of you for a cocktail in a house that is on that scale. The areas of the two are about 10 to 1, right? But let's put numbers on it. Greenland is about 4 times the area of California, okay? So 4 Californias covered in between 1 and 2 miles of ice, right? That's kind of cool. And Antarctica is 1.5 times the United States, all right? So bottom line is, if all of the ice were to melt, from Greenland, sea levels would rise 23 feet and about 10 times as much for Antarctica, right? Sea levels there have been many times in Earth's history where there has been no ice. So sea levels have been this much higher in the past, all right? But this is what we call the potential, all right, contribution from the ice sheets. Okay, that's cool. All right, so let's put some science figures on it. Gotta have a time chart. This map is one of the stunning results from a satellite, a NASA German partner satellite called GRACE, which Dr. Famulietti will speak about in his talk. Okay, and what is plotted is it's a strange thing, but it's what they call the equivalent centimeters of water. Okay, so it's the change of mass everywhere on Earth, and mostly attributed to a change in the amount of water that's stored there. Okay, so if you just focus on Greenland and the West Antarctic ice sheet, what you see is what my colleague Bill Pazzard calls the bullseyes. Okay, so blue is negative. It's the equivalent to here 5 centimeters per year. So imagine what I said: 4 Californias losing 5 centimeters of ice every year. That water is just flowing into the ocean. All right. So if you add up the total contribution from Greenland and the total contribution from Antarctica, you get these two curves, which show over the last 10 years what I would call a pretty steady decrease in both. Right? Some people want to make hay and say it's gone up, but that's pretty controversial. The record's a little short. But, right, okay. I'll make this point now. I'm not sure when I'm going to make it. Now seems like the right time. Before 2003, we didn't know what this number was. We didn't know whether Greenland or Antarctica were gaining or losing mass on the whole, right? I mean, Antarctica is bigger than the whole United States. 1 to 2 miles of ice. Humans have no ability to monitor that to the level that we need to understand sea level rise until 2003. 2003 was really the year when GRACE began to give us, the GRACE satellite began to give us this data. So in fact, it was revolutionary in climate science, all right? And fortunately, GRACE still lives, and its successor is in the works, right? So NASA, all scientists basically who work in this field, understand that this is a fundamentally important instrument. So we'll be carefully monitoring what's happening on these ice sheets in the coming decades. But not only did we not know whether these ice sheets were losing or gaining mass, we also didn't. Every other reconstruction we had before said that they were mostly stable. Okay, a little bit of melting, because we're still getting out of the last ice age. Okay, but I got it. Yeah, but mostly stable. The fact that they are going down at this rate was a surprise. So if I just click, was a surprise, and we'll get back to it in a minute. Okay. Now, just to conclude the third piece of the pie, excuse me, the melting mountain glaciers. This is what it looks like. Okay. The bigger the circle, the bigger the amount of mass being lost. Okay. Put together by one of our colleagues at JPL. So you see the Himalayas, Patagonia, the Alaskan mountain glaciers, the Canadian Shield, the Rockies, what's this, Svalbard, other small islands in the Arctic. Of course, the Alps are melting. And Iceland. You think Iceland is, no, Iceland's is the of course. That's all it does is melt. And the Andes. So, this is what it looks like, and we can draw another plot, and it shows, like, the polar ice sheets, a net loss of mass over the whole record. Okay, so this is a good time to transition. From everything I've said before, I hope you are convinced that we now know that over the last few decades, the melting of the polar ice sheets has accelerated. And now is significantly contributing to sea level rise. And that's the point I want to make here. This second doubling, we attribute almost all of that to the ice sheets, all right? But no one anticipated that. It's not like the climate scientists sat around and said, in 1992 or thereabouts, the ice sheets will begin to go. We knew theoretically that the ice sheets would melt. But when they're going to go and how fast they're going to go, we had no idea. All right, it was just beyond our ability to make a good estimate. Now we know how much they're going because we're able to observe it. So that's great. But we actually have no idea what they're going to do tomorrow. This is the state of the art is what the heck is going to happen tomorrow? No idea, all right? But so how do we make progress, right? We're scientists. We have all the tools available to us to investigate this problem. One of the directions of research is motivated by this second paragraph, okay? We know that the oceans close to these ice sheets have warmed, but we don't have very good, so the oceans are implicated in some of this melting. But the reality is we don't have very good measurements of the ocean around these ice sheets. Not hard to imagine why. They're huge, it's cold all the time, right? It's just hard to get there, right? The oceans are covered in ice 3/4 of the year, right? It's insanely expensive and the area is huge, all right? So we think the ocean is implicated, but we actually had very few measurements of the ocean temperatures and the currents around the ice sheets. So it makes a good hypothesis, but it doesn't make an answer, that's going to satisfy a scientist. So, when I said we have no idea what's going to happen, I like this curve here this plot here on the left, because it tries to convey a sense of just how much we don't know, all right? And so here's sea level from 1700 until today, okay, that's the end of this record, right? Now, if you recall, the total to date has been since 1900, has been about 8 inches, okay? So now our scale is in feet. I changed it from meters for you fine people. But here we are, 1 foot, more or less, is what we've had today. So in the next 84 years, which is just a time that we arbitrarily pick when we make these plots, right? We could go out as far as we want. It's not like global warming is going to stop in 2100. By 2100, there's a range that says 4 feet, or 1.5 feet to 4 feet. Okay? No, that's 100% uncertainty. And there are plenty of scientists who will go on record and say that these numbers are absurdly conservative. And the only reason they are this low is because consensus documents, they're from consensus documents, right? So if you have some scientists who their reading of the tea leaves is a little bit more, is different than the rest of the group, they don't get a say in this forecast, all right? But they come out, they write papers. James Hansen, he just had a paper recently that was controversial in its extreme projection, okay? The bottom line is, and the truth is, we don't know what it's going to be, right? So we're motivated. And okay, so got it. Now, so what are we going to do about it? Well, what we're doing about it is we recognize that we don't have enough data for this hypothesis that the oceans are involved in melting of the ice sheets. So, so until we can relate, let me just step back for 1 second. Right. So we can measure the melting, but we can't predict it or explain it until we have these data. Okay. Until we have these data about what the ocean is doing, we cannot make useful predictions about sea level rise as the world continues to warm. And I've got 10 minutes left, so I'm going to move quickly through the next couple of slides. The first slide is 3 minutes left. I had 10 minutes left 7 minutes ago. If you get bored, I'll just stop, but otherwise I'll continue. You guys seem like you're on board. This is just a nice schematic, from a 7th grade geography textbook, showing an ice sheet in the climate system. Okay, and the point here is that along much of its periphery, it's in direct contact with the ocean. All right, around Greenland, it looks like this. In the southeast and the central west and northwest and north of Greenland, this is what you see. Actually, when you fly from LA to, say, Rome, sit on the left side window seat, you'll see Greenland. It's cool. And it won't be quite as close as this, but you'll see glaciers and you'll see the fjords. Okay, so that's what this is. This is a glacier that's flowing down from the interior. All right, it's a river of ice. And this one here we call a tidewater glacier because when it ends in the ocean. Okay, that's very interesting, right? These fjords, of course, were all carved out in previous ice ages by much, much larger rivers of ice that scoured through the terrain. But now they're filled with water. This fjord, for example, is more than 1,000 feet deep. All right, just filled with water, a giant U-shaped valley into which the glacier flows. When you're on a boat sitting near one of these glaciers, looks like this. I mean, maybe some of you have been to see glaciers on a cruise, but it looks like this. These are some seabirds just for scale, right? So we got maybe 150 meters above the sea level. right? And this one goes down, what is this one? 600 meters down. So almost 2,000 feet down is ice. So it's a wall of ice. All right, it's pretty amazing. This one here is about 3 miles wide. Right, 3 miles wide, 2,000 or so feet high, right, entering into the ocean. I have to skip this slide. Right. Okay. So the circulation of the ocean around Greenland looks like this. Okay. And the red arrows are okay. The red arrows show that the water is warmer. Okay. And what you see is this is the Gulf Stream. Okay. Waters are warmer in the tropics. They're taken by the Gulf Stream currents to the north. All right, and these currents, some of them come up to the Arctic Ocean. Some of them almost get to the Arctic Ocean, turn around and hit northeast Greenland. And some of them swing around here south of Iceland, come up the west side. Okay, these are the main currents that bring the heat that's implicated to the melting of Greenland to Greenland. Right. So, so it's those waters that we're going to measure. Okay, this is the last 2 minutes of my talk, even though I got the 1 minute warning, will be about this new mission, which is named Oceans Melting Greenland, or OMG. I take no credit or blame for the name, but I love it. I love it. It's fun, right? It's fun. It's true. Our colleague Josh Willis at JPL made the logo, which I think is artistic. Off the record, this is not the official NASA approved logo. NASA approves the name, but thought the logo was a bit much. But I know. Doesn't make any sense to me either. But this mission, this is a new mission, okay? And we have 3 components. 3 components. The first component is to measure the changing elevation of the glacier. Okay, glaciers are melting, they get thinner, right? Their elevation goes down. So one component is to measure the change in elevation. Another, at very, very great detail. Another element is to measure the ocean temperatures, okay, on the continental shelf and in the fjord. And the last component may seem esoteric, but is actually central, is the measurement of the seafloor, the topography of the seafloor around the island of Greenland and in the fjords. Okay? And the reason that's important is that the warm waters that come up and melt the glacier, they're far below the surface. So you need to have a really deep fjord for the warm waters to get to the glacier. But it turns out of the several hundred fjords of Greenland, only like 6 of them are mapped. Right? Because who cares until now? So that's a big part of the mission, mapping the seafloor. And that will probably be one of the biggest legacies of this mission, because the seafloors aren't going to change that much, so future generations of scientists will be able to use those maps. All right? So we're going to make measurements of the ocean temperatures every year for 5 years around the island. We're going to map the seafloor in several sites where we think the glaciers might be particularly vulnerable. All right? And we're also going to map the changing surface elevation. All right, because the idea is, I'm going to have to leave this up. You can read it if you want to have to talk. The idea is that we will go around Greenland every year for 5 years, measure the ocean temperatures, also while simultaneously measuring the glacier elevations. And hopefully, if the temperature goes up, the elevation goes down, and we'll be able to make some quantitative estimate of that relationship. Okay? Like I said before, getting to Greenland is very difficult. It's very difficult to take ocean measurements there. So we're going to use a NASA jet, a Gulfstream 3. Some of you have a Gulfstream 3, I see. It's my first time in one. It was pretty cool. What they do is they put a porthole in the back of the jet, okay? And we have an instrument that's like a torpedo, all right? It has a parachute and a radio transmitter, okay? We fly around Greenland We deploy the torpedo, parachute goes up, it descends down to the sea surface, hits the sea surface, okay? And then a part of it stays at the surface with the radio transmitter, and a part of it descends down to the seafloor on a wire. And as it goes, it has a thermometer. Okay, so it measures the ocean temperature and salinity on its way down, and it transmits the data back to the plane, which is circling overhead. Okay, so we're going to do that every year for nominally 3 years, but probably 5 years. And we do that at 250 locations on the continental shelf and in the fjords when there are no icebergs. That'll be that project. That our first part of that campaign begins in September of this year. The second part of the campaign, I said, is measuring the surface elevations of the ice. We use probably the same Gulf Stream with a radar package mounted to the hull. Okay, and that flies close to the glaciers, get us those maps. All right. And the last component, like I said, is the measurement of the seafloor. Sonar from a ship, send the ship up there. And this other component is to use an airplane using a method which is too complicated to discuss. And the remaining 1 minute that I have. I know. All right. All right, I'm on my last 3. I apologize for keeping you. This was this summer. Okay, this summer it was the first ship-based campaign. It was a great success. It was 40 days at sea. I wasn't able to go on board, but I was able to get my younger brother a job as a deckhand. Not a deckhand. He was actually, that's a total exaggeration. He was deploying the science instruments too. You know, he was a great help. 40 days at sea. He got on the ship in Maine, traveled to Greenland, spent 40 days, starting off down here in a little village called Aasiaat, and steaming all the way up here till Melville Bay. You know, they visited dozens of glaciers, took hundreds of ocean measurements, mapped 7,500 kilometers of the seafloor. It was a great success. Okay? We will repeat that for Southeast Greenland this summer. Okay? Yes. The second component, the only other component that has completed, right, just completed a few weeks ago, was the radar, airborne radar. It came here, visited us in Palmdale at the Edwards, I think it's called Edwards. Armstrong, is it? I can't remember now. Edwards, right? Edwards. Came, visited us here at Edwards. It flew all around Greenland. And this is very difficult to see on this map, but this is basically the radar returns. So from these maps, we'll be able to reconstruct the surface elevation. All right. So that is the conclusion of my talk. These summary slides are there for your enjoyment, if you'd like. Thank you.
All right, we've got a little over 5 minutes for questions. If you raise your hand, I'll bring the microphone to you.
I'm curious about whether or not volcano activity on the ocean floor has any effect on warming in that particular location, because your warming was not even.
Yeah. Well, volcanoes definitely have an impact on the temperature of the air temperature. So, you know, we can go back and find these major eruptions throughout history and even recent history and find cooling of the atmosphere in the years following the eruption of a large volcano. For the ocean, I don't think that there's enough variability in underwater volcanism to drive fluctuations of the whole global ocean. But we do, just as a side note, you do need to include underwater volcanoes when you run an ocean climate model to get the ocean temperatures correct in the deep, deep ocean. But so I'm not aware of any research in the direction that you inquired about.
questions? Yeah. And then we'll go back.
You noted the Gulf Stream coming up to bring warm water to the Greenland area, and you said the warm water is very deep. Warm water usually goes up to the top. What's going on?
It's a great question. It is, yeah. Well, warm water, warm things, because they are, I guess, expanding, right? They're more buoyant, right? If you in a typical situation of
Less dense.
you could say less dense, yeah. In a typical situation, if you cool water at the surface, it will get denser and sink, right? Similarly, if you heat up water from below, it'll rise. But that's true in the absence of salinity. So around Greenland, the key factor is that the upper few hundred feet of the ocean is very, very, very fresh. And that freshness can be traced to the Arctic Ocean. There are, I forget the number, but there are a tremendous number of rivers that terminate into the Arctic Ocean. The Arctic Ocean, actually, the surface of it is very fresh. So when those waters flow out of the Arctic Ocean, mainly through, say, Fram Strait, the passage between northeast Greenland and the island of Svalbard, those very fresh waters, they stay on the continental shelf. They circulate around the whole island. They make kind of a very, very less dense layer. So when the warmer waters from the Gulf Stream approach it, those waters are actually very salty. And the reason they're salty is because on their several thousand-mile transit from the tropics, they have evaporation has been taking place the whole time, right? They've been evaporating, giving off heat, latent heat, to the atmosphere. So the warmer, saltier waters approach the cold, fresh waters. The freshness wins. The warm waters sink down. Yeah. Good. That's a very good question.
Okay, somebody over here?
I don't know if I can articulate this clearly enough, but going back to, thank you, going back to since 1950, warming was on the increase. And you said something about only 10% of, and I'm missing the word after of,
Uh-oh.
only 10% of. And I don't know if that's as clear, probably as clear as mine.
We can go over the slides at lunch, and we'll find that the 10%.
All right, thank you.
Yeah.
Okay. All right, George?
Could you comment on nonlinear and tipping point events that might cause large sea level change, and how likely they are and how big they might be?
Wow. Yeah.
You know,
Well-
there's a lot of paper about that lately.
Yeah, there's a lot in the paper about that recently. Okay. Yeah, well, there is one of the tipping points that people investigate is the collapse of the West Antarctic ice sheet, and the reason it's not that complicated. Actually, a lot of the West Antarctic ice sheet is below sea level, so much of the ice is actually way, way below sea level, right? And there's this idea that if the seafloor slopes down, okay, this is the ice shelf flowing from the center of Antarctica, flowing down to the ocean, creates an ice shelf. If the seafloor of the grounded ice tips back down, okay, and you perturb the front of that ice shelf, so if you push it back a little bit, right, if you melt it back a little bit, say, well, now all of a sudden there's more surface of that glacier that's in contact with the warm water, all right? So there's a positive feedback that can kick in and drive that edge of that glacier, the front of that glacier, back all the way down where the seafloor slopes inward, I guess, all the way down. So that would be a positive feedback. You wouldn't have to do any global warming at that point. The system will just run away until the seafloor levels off again. But that leveling off again could be a few hundred miles upstream. So there's the potential for a relatively rapid loss of a tremendous amount of the Antarctic ice sheet, if this feedback kicks in, that would be a tipping point. But it's the rate at which it would happen, nobody knows, right? Some authors have suggested that it has already begun, right? But sea levels aren't 20 meters higher everywhere tomorrow, right? So the feedback process can kick in, but it takes a while for it to evolve. We could talk about potential tipping points all day, but that's just one that's relevant to this, germane to this topic.
Okay, I think we probably ought to break at this point, and thank Ian again. Ian will be here for lunch, so if you guys can all ask him questions during lunch, if you haven't gotten your question answered.